Perfect. I think we are right. So today we'll continue with Redox, and we will do some questions on Redox, and we will do some important concept of Redox, which is basically the equivalent weight part, or I would say the normality part. Okay. So let us continue this without wasting any more time. Tell me, have you all done these questions? Question number 1 to 10 from Redox. How many of you have done these questions? Raise your hand. Hi, Kaustov, Victor, how are you? How many of you have got chance or time to do the questions? Pranav has done the questions. Pranav BP has done. Abhishek has done the questions. Interesting. Yes, in-text exercise 2, Victor. Everyone who has done the questions, exercise 2, in-text exercise 2, these 10 questions, please raise your hands immediately so I can just get an idea of how many of you have done. So Pranav, Abhishek, Pranav, Shagritaya, and Vittal. Okay, where is Abhay, Vittal? I don't remember seeing Abhay yesterday. Abhay was there in the class?
Sir, I'm not sure.
No, even I'm not sure. I just forgot. I think Anirudh joined. Okay. Perfect. ठीक है. Guys, okay, it's all right if you have not yet done these questions, okay, but you know, मतलब, when the concept is fresh, doing these questions in less time is easier. When the concept becomes a little bit stale, then it becomes a bit difficult to recall it, and you have to just figure out, okay, what did sir say? Like, did he tell us to do electrons on one side, ions on other side, oxidation number? So all these things will just start getting complicated if you let off too much of time. These 10 questions are technically not very complicated. Yeah, right. Pranav, Abhishek, Pranav, Vittal, can you tell me, like, do you have any doubts in these questions? Any specific ones? We can discuss that one first. Guys, any doubts?
Yes, straightforward.
Yeah, pretty simple,
Fine.
right? Okay, so yeah, that's the whole thing, right? The reason I wanted you to solve this question was because it's technically direct application of what we did yesterday. Okay, so let me just do one thing. Since we are here with a plan to do some questions, let us focus on question number 10 for the time being. All of you who have not solved in-text exercise, please look at the question number 10 and try to find out what should be the coefficient of oxalate ion in the following reaction. Now, for those who have done this question, let me just give you one question. Give me a moment. Let me give you a question. Those who have done it, give me 1 minute. Those who have not done it, please start doing the question number 10. So this is technically, I would say Redox is like one of the most basic thing required if you want to do like any chapter, like say electrochemistry, or say Mool concept, the complicated part. Okay, so after this session, I will technically need one more session. Okay, to finish off this chapter. But the reason I am going a little slow with this one is because I want to ensure that we don't miss out on anything. Okay, and also we are having exams going on like simultaneously, so I don't want to pressurize you with anything. So just it's a relax, do some do some balancing questions, that kind of a stuff. Okay, so Let me give you a very simple, interesting reaction. This looks good. So by the time rest of you are doing question number 10, those who have done exercise 2, please do this question. What you have to do, obviously, balance the question, balance the reaction. For those of you who are parallelly on phone and PC, can you just check if the live is going on properly and if the audio is correct there? I generally forget to check the. Yeah, we are live for sure. So mostly all my students who come live, who like joining the live sessions, are generally having their classes sessions in the afternoon. So that's one of the reason most of them are not able to join in the afternoon. But yeah, they get to see it afterwards. But soon I'm planning to go live even in the evening. But I have to figure out a plan of action because definitely I cannot like go over the complete chapter in the evening. So I'm just planning to come up with some good, kind of a habit of maybe go with like 5 questions daily. Daily 5 questions. We'll do 5 questions. Like again, commitment is the difficult part. But I want to do that. I want to eventually commit with like something like 5 questions every day, maybe 9 o'clock. I'll just come do some 5 questions, whatever topic currently going on. Yeah. 28 students are here. We have Akash, Abhishek, Amrita, Anaga, Anirudh, Chinmay, Dhriti, Diya, Gauri, Ira, Kaustubh, Kridhar, Meera, Nainika, Nihant, Niyantri, Omkar, Pranav, Shreya, Shreyas, Soumya, Shrivardhan. Where is Shrivardhan? C. Vaishnavi and Vittal. Shrivardhan C is missing. Then Abhay is missing. Then Sanvi missing. It's all right. That's the reason we are going live. So that even if you in case miss out this one, this is an important session. It's an important chapter. Okay. Answers, guys. If you are ready with question number 10, first answer question number 10. And if you are done with that, then we will move on to question number 11. What do we have to do? We have to balance these chemical reaction using our understanding of redox. Okay. Omkar needs help with the oxidation half of the question. Okay, no issue, Omkar. So we are talking about question number 10, Omkar, right? That's the one we are. Yeah, perfect. Okay, so about question number 10 first. Uh, MnO4 minus is going to Mn plus 2. If you remember this, we have already done this question yesterday. How many of you remember this? If you remember, the first question I did was on exactly this thing, KMnO4 reacting with oxalic acid, H2C2O4. Yeah? And it was converting in and H2SO4 maybe. Then you were getting MnSO4, K2SO4, CO2 plus H2O. Do you remember this question, Omkar?
Yes, sir.
What I'm trying to say is, when you go back uh, after the class, just take out like 15 minutes, like before you go to sleep. So once you take out that 15 minutes after a class, maybe a morning class, afternoon class, evening class, but before you go to sleep, for 15 minutes, just go over what you did in that class on that day. So once you get the idea of what you did on that day, you will, I don't know, it does not work on a very conscious level, it might not work, but on the subconscious level, your thought, your signal, the new, neural network that just got formed, that gets a bit stronger, it strengthens up. So before going to sleep, it is very important whatever you did in that day, take out 15 minutes just to go over whatever was covered. And this is for all the subjects. Okay, this is for all the subjects. That way, it's just like you will be saving a lot of precious time, because this kind of a same question just twisted in a different bit. Carbon in C2O4 you can see is in +3 oxidation state as we did it. So I think it is pretty simple. All of you should get this answer correctly. Please do ensure that, because it's I'll take the attendance now. Yeah. About the second question, how many of you have got the answer for second question? Pranav, Vital.
So the second question of exercise 2.
No, not exercise 2. The one that I just. Oh, my screen is not shared.
Sure.
Arey, teri. I thought my screen is shared. Guys, please. I really thought my screen was shared, so too many things now simultaneously managing the Google Meet, YouTube. I forgot my screen was not shared. Okay, this is the second question. KBRO3 reacts with KBr and HCl to form Br2, KCl and H2O. Yeah, you have to balance this question.
Sir, actually, I got that question. Like,
You got it?
yes, sir.
Yeah, send the answer in the message.
Sir, no, sir, I was talking about that exercise question, not this.
Which question?
10th one.
In text exercise, right?
Yeah,
So the MnO4 minus C2O4 2 minus that question,
yeah,
right?
that one.
So we did it already. That's what I was saying. We did that already, right?
Yes, sir.
Did you find it, Omkar?
Yeah, I got it, sir.
Got it, na? Okay.
So could we do the fifth question of in-text exercise too?
Sure.
Thank you, sir.
All of you are able to see the in-text exercise questions. Perfect. So we'll also discuss this question number 5. Okay. So those who are done with question number 10, please go over question number 5. All of you have the in-text exercise. So we'll be doing question number 10. No, we already did question number 10 yesterday. What is the answer for question number 10?
Sir, 5.
5,
Three
right?
options. Yes, sir. 5.
And for MnO4 it was 2, right? So 2 KMnO4 reacted with 5 H2C2O4 and we got the product. So answer in this case is D5. Let's have a look at question number 5. The ratio of coefficients of HNO3, FeNO3 hold twice NH4NO3 in following redox reaction. So let me just write down the redox reaction loud and clear. It is iron reacting with HNO3, which is your nitric acid, thereby producing ferrous nitrate, ferrous because it is +2 oxidation state, ammonium nitrate along with water. So this is the reaction that we are dealing with. Now in this reaction, if you can see it very clearly, what do we have? We have iron in zero oxidation state because it is in elemental form. Then you have HNO3. In HNO3 you have nitrogen in +5 oxidation state. Now it's a very interesting question. Now think about it in a way. The nitrogen, iron is going to get oxidized from 0 to +2. Pretty simple. The nitrogen in this case is going from +5 to -3. Can you name the compound in which nitrogen is going to -3? How many of you know the compound where nitrogen is going to -3? Pranav and Akash has already sent the answer. Okay, perfect. Abhishek has also sent the answer. Amazing. Abhishek, your answer can be divided by 2 and yet, you know, remain in a ratio, same. So just check your answer, Abhishek. So, how many of you know which ion or which compound has nitrogen in -3? Obviously, these are nitrates, so nitrates cannot have nitrogen in -3. They are nitrates. We already found out its oxidation stated as +5. First thing, guys, any of you, let's start with that. Any of you is finding difficulty in figuring out the oxidation state of the element, please let me know. I need to know that very clearly. Trust me, if you have, not in this question, maybe some other question, maybe when you are practicing, if you have a problem in finding out oxidation state of any element in its compound form, please raise your hand so I will know it. I will try to help you out accordingly. Okay. If you are finding any difficulty in finding out the oxidation state, do let me know. And if you don't feel shy about it, if you are feeling shy about it, then message me after the class. It's fine, okay? But I want all of you to be very much, confident with finding out the oxidation state. If you are not able to do that, then it's my failure as a teacher. Please understand that very clearly. Now, because it's a very basic concept and I want everyone to be 100% sure when we are doing that. Now, in this case, ammonium ion, as you can see, is the only one where your nitrogen is in -3 oxidation state. Can you see ammonium? It is NH4 plus. Whenever hydrogen is in a compound, Perfect. NH3, yes, Pranav, perfect. Ammonium dichromate, Meera. Yes, we did it, right? Ammonium dichromate we have done in the class. You remember that, huh?
Yes.
Right. So in nitrogen, in case of ammonium ion, nitrogen has to be in -3 oxidation state because there are 4 hydrogen which are in +1, +1, +1, +1, which means the total charge to be +1, 3 +1 has to be cancelled out by -3 of nitrogen. Now the beauty of this question is one of the nitrate ion will get reduced to ammonium or will get reduced from +5 to -3, whereas rest of the nitrate will remain as it is just as an ion in the question. Okay, so let me just write down the half reactions for this. So the half reaction is Fe forming Fe plus 2. Obviously, along with that, it will produce 2 electrons. So this is my oxidation half. On the reduction front, we have NO3 minus converting into NH4 plus. Now we will focus right now only on the oxidation state, not on oxygen and hydrogen. Okay. So from the oxidation state perspective, nitrogen is going from +5 to -3, which means it is going to accept electrons. How many electrons? It has to accept 8 electrons to go from +5 oxidation state to -3 oxidation state. Whereas iron going from Fe to Fe plus 2 will lose 2 electrons. Let me write it like this. Okay, so iron is supposed to lose 2 electrons, nitrate is supposed to gain 8 electrons. So if I want to balance this reaction, should I not multiply the first part, the iron part, with 4? Are you all in the same page, on the same page with me? Iron,
Yes, sir.
perfect. So iron losing out 8 electrons, nitrate gaining 8 electrons. Beautiful. Now, what is the ratio that I am getting? I am getting a ratio that for every nitrate ion getting reduced, I will require 4 iron atom getting oxidized. So keeping this ratio in mind, I will write down the redox reaction. Let me take it below. So I will write it like this. Say 4 Fe reacts with 1 nitrate to form 4 Fe plus 2 plus 1 NH4 plus. Now this is redox reaction. This is balanced redox part. Now what I will do, I will introduce the rest of the ions in this whole equation. So the nitrate in our question came from HNO3. So I will just introduce H over here. So we will have HNO3 one molecule. Then iron after reacting got converted into iron nitrate. So for every iron we will require 2 nitrate ions, and for every ammonium ion we will require 1 nitrate ion, and along with this we will require water. So the sky blue is the one which we have yet not balanced. Okay, now let us think of it like this. The nitrate which was supposed to get oxidized, which was supposed to get reduced, has been used up. So nitrate which was supposed to get reduced is this nitrate, and this got reduced to ammonium. That's all right. But we need more nitrates, right? You can see nitrate over here, nitrate over here. For this, we will require extra HNO3. Now, this HNO3 is not involving in the redox. It is just there to counter the opposite ions. Okay. So, in case of iron, if I just want to write it down, in case of iron, so this is the straightforward 4Fe. In case of HNO3, let me just calculate the number of HNO3 after this whole thing. For iron, I will require 2 nitrate for every ion. So this is twice, and this is 4, and 1 ammonium nitrate as it is, and water. Let us balance the water from the above reaction. Let's balance it over here. So how many nitrate are there on the right side? There are total 5 nitrate ions on the, sorry, 4 into 2, 8 plus 1, 9 nitrate ions on the right side. So these 9 nitrate ions are just there to, compensate the charges. Okay. Whereas one nitrate ion was the one getting reduced. Got it? So there are total 10 HNO3 molecules on the reactant side. On the product side, I think iron is balanced. Ammonium nitrate again also balanced because only one ammonium has to form from using 4 iron atoms. So that's also sorted. We'll think about the hydrogen once we mention 10 HNO3 over here. Now all the hydrogen that are present on the product side are with water only. So I will simply write down 5 water molecules. Let us have a look at the reaction and see whether it is balanced. We have 4 iron. Yes, 4 iron on left and right hand side. There are 10 nitrogen on the reactant side, and you can see on the product side there are total 10 nitrogen. So nitrogen also balanced. Hydrogen, I missed something. I missed the ammonium ka hydrogen. I missed this hydrogens. Okay, I missed this hydrogen. So that's the mistake. So there won't be 5 water molecules. 4 hydrogen has been used up over here. So out of 10 hydrogen, 4 got used up over there. So we can have only 3 water molecules. Now let us check the oxygen, because oxygen will actually give us the idea if our reaction is balanced. So left hand side, right hand side, let us look at the oxygen. On left hand side, we have 10 into 3, 30 oxygen straightforward. On right hand side, let us have a look. So 3 into 2, 6 oxygen in the ferrous nitrate, and there are 4 molecules. So 6 into 4, 24, plus ammonium nitrate 3, plus water molecule 3. So that brings us to 30. So we have 30 oxygen on the left hand side, 30 oxygen on the right hand side. So now this is the reaction, which is our balanced chemical reaction. Did you get it? Is it clear to everyone? If it is clear, just message me a clear in the message section, in the chat box, on the YouTube, anywhere, please. Done. Shreyas, Anirudh. Vittal asked this doubt, right? Vittal, you got it cleared? Akash, clear? Perfect.
Yeah.
Okay, perfect. Okay. Aditi joined late. Yeah, Vittal.
Disconnect in the middle somewhere. Could you explain the adding HNO3?
You understood that part, right? The HNO3, which is just to cancel out the ions or the compensate the ions on the right hand side.
Oh, so you can just add HNO3. So could you explain that?
I said, look, this HNO3, let's put it like this. This is part of the redox reaction. Okay, this is your redox reaction. How did I get it? I just saw that, okay, iron will produce 2 electrons, whereas every nitrate ion converting into ammonium requires 8 electrons. So these are my oxidation half and reduction half. Okay, now for every nitrate ion getting reduced to ammonium, I will require 4 iron atom getting oxidized. Did you get this part, Victor?
Yes.
Perfect. So now, once we are done with that, we are done with the major thing. We got this, this ratio of redox reaction. So this is a redox reaction. Now, all the ions which are present in the sky blue color, they are all added after that, because they are not part of redox reaction. They are just, balancing the ions on both the sides. That's the whole idea.
Yes, I got it. Yeah.
Yeah. Cool. Even if you don't get it after that, then just go back to YouTube. You will have this recording live just after the class. Okay. Cool.
Yes.
I was saying, Aditi joined later. Aditi, did you get chance to do the exercise 2?
No, sir, I don't think I mean, I was just looking at what you were doing, but
Yeah. No issue. So please complete this exercise 2 whenever you get time. Okay. Try to do it
yes.
like it won't take you more than 10-15 minutes. They are all very simple, straightforward questions. Okay. So cool. Let's move on to question number 11. I can see Pranav, Akash, Abhishek have already finished off the all the three Pranavs, and Akash and Abhishek have already finished off question number 11. So I want all of you to just go over question number 11. Till then, I am getting one more question for you guys. Mm, let's play around with KBRO3. So there's another question. I hope it's visible. Yeah. So those who are done with question number 11, please move on to question number 12. We have another question on the board. Pranav has already moved on to 12th. Abhishek as well. Perfect, perfect. Akash, perfect. Pranav, perfect. Akash done with the done. Pranav has Praveen Kumar has answered. Pranav has answered 14th. Yeah, not 13th. Take it. Good. How many of you are done with question number 11, or are having like just raise your hand if you are done with question number 11. Come on, everyone, fast. Raise your hand if you are done with question number 11. Question number 11, hands raise, everyone hands raise, fast. Akash and Abhishek also done, right? Aditi, Amrita, Anaga, Anirudh, Chinmay, Dhirati, Diya. Everyone who are done with question number 11, KBRO3, the first question. If you are done with this, raise your hand. All the three pranavs are done, right? Oh, even after you raise the hand, you are saying will meet, I tell you. ठीक है. Niyan 3, did you get it? Do you want me to help with that? Question number 11. Niyan 3. No, Niyan 3 is done. Yes. Ira, did you get it? Question number 11. If you want me to help, let me know. So let me show you the answer. You finished it? Beautiful. Beautiful. So the answer for question number 11 is 1 5 6 5 6 3 6 3. I suppose all of you are getting this. If you have doubt, do let me know. Otherwise, you can all lower your hands. Perfect, perfect, amazing, amazing. So if you have a doubt, do let me know. Huh? Okay. I will tell you the answer for the next question, which is question number 12. So question number 12, it is 1 3 1 1 1 3 1 1 3. Everyone got this? 1 3 1 1 1 3. Question number 12.
Yes.
Yeah. Okay. Omkar needs help with this one. No problem. So in this one, Omkar, we have KbRO3. Did you find the oxidation state of bromine in KbRO3, Omkar? Seven? No, no, dude. Omkar, go back and try those 20, 21 questions I gave you for, finding out the oxidation state. Do them once again. Potassium is in +1 oxidation state, oxygen is in -2 oxidation state. Let's suppose bromine is in X. So 1 plus X minus 2 into 3. This should total become 0. That gives my bromine +5 oxidation state. Okay. And bromine on the right hand side, you can see is in -1 oxidation state. Let us have a look at arsenic. Arsenic is from the nitrogen family, nitrogen, phosphorus, arsenic. And right now, arsenic is in +3 oxidation state. Safal, hi Safal, how are you? We are doing redox, chapter redox, and we are doing balancing using redox. Okay. Now, arsenic is going from +3 to +5 in H3AsO4, which is just like H3PO4. Arsenic is in +5 oxidation state. Omkar, now that I have done this oxidation and reduction part, can you further continue with the balancing? Do you need me to help more? Omkar, please confirm. Yeah, you will manage. Okay, write it down. If you find it difficult even afterwards, let me know. Okay, sure. So let us focus on next question, which is question number 13. In this question, we are reacting tin with HNO3. Just to remind you, in the previous question, we reacted iron with HNO3. Now, HNO3 is a very amazing, acid. So its behavior with different elements is one thing which is common is it will oxidize the element, and as a result, sometimes it produces NO2 gas, which is a brown colored gas. As in this case, you can see when you add HNO3 to tin, you will get tin oxide. Now, can you see the oxidation state? Let me first give you the answer for this question. For this question, the answer is 1 4 1 4 2. Okay, perfect. 1 4 1 4 2. Did you get it? Did you all get this? How many of you got question number 13 correct? Please raise your hand. All of you who got question number 13 correct, please raise your hand. Amazing. Amazing, guys. 21, 22 hands are there out of 32, 23. Amazing. Anyone needs help with this? Do let me know. If you need help, I will explain. I will solve this question. Please message me if you need help. Okay. can we call reaction 11 to be a disproportionation reaction? The reaction 11 has bromine in +5 oxidation state and another bromine in -1 oxidation state coming together to form bromine in 0 oxidation state. So whenever you have disproportionation, disproportionation is breaking down of an atom, or I would call it self-redox, where one atom itself is getting oxidized and itself is getting reduced. So that is disproportionation. But when we have two different oxidation states coming together to give only one oxidation state, we call it conproportionation. Okay. So this is opposite of disproportionation. Okay, Pranav? Perfect. Amazing. Cool. So yeah. In question number 13, as you can all see, the oxidation state of tin is changing from 0 to +4. Like the highest oxidation state that tin can achieve is +4, because tin belongs to carbon family: carbon, silicon, germanium, uh, tin, lead. Okay. Whereas in this case, HNO3, which is right now in +5 oxidation state, is going to NO2, where nitrogen is in +4 oxidation state. So you can see like HNO3 requires one electron, so it will take one electron, whereas tin is giving off 4 electron. So since tin atom is giving off 4 electron, for every tin atom getting oxidized to +4, you will require 4 HNO3 molecules who will take one electron and get reduced to NO2. Now, this is the very interesting part of the reaction. Reactions of metal with HNO3. Whenever you have concentrated HNO3, you will get NO2. So, whenever you have concentrated HNO3, HNO3 is going from +5 to +4. Okay. Now, for +5 to +4, there is only change of one electron, whereas the oxidation state of tin is going from 0 to +4, which means it is giving off 4 electron. Now in this process, I will just say HNO3 is the one which is taking the electron, which is forcefully removing the electron from the tin. Now if I reduce the concentration of HNO3, or if I reduce the total number of atoms of HNO3, molecules of HNO3, what will happen? HNO3 will get diluted. So whenever HNO3 gets diluted, we might not get NO2 as a product gas. In some of the cases, we get N2O. So we will talk about this in detail when we talk about the reactions of metal with HNO3. But to give you a generic idea, metal, when react with concentrated HNO3, will produce the brown colored gas NO2, whereas in some cases, when metal react with dilute HNO3, instead of NO2, you get the N2O, which is laughing gas. If you know, the nitrous oxide, which is also used in Fast and Furious in the cars for nitro boost, right? So in case you have dilute HNO3, you will get N2O as a product, whereas in case of concentrated HNO3, you will get NO2 as a product. So things like this can be determined using the understanding of this chapter, Redox. It's very important from that perspective. Taking it ahead to question number 14, let me just write down the answer for question number 14. As I can see, everyone is getting the same answer. So 1, 2, 2, 1, 2. All of you are getting the same answer? Tell me if you are all getting the same answer. There has to be one more thing. I think we are missing on the hydrogen. We have to have water over here.
Yes.
Yeah? We need to have water over here. There's no water molecule on the right hand side. Where are you going to put the hydrogen? Yeah? So what will be the water? I just want you to check it again now. Please check it again. I think initially I forgot to write the water molecule. Please check the whole reaction again.
Sir, actually, I got that question, so thanks for explaining.
Which one?
That 12.
Amazing, 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 Omkar. After this, we will move on to the next part. Okay, I need like 15-20 minutes to just explain that part, and then we'll end this session. Whenever you get time after this, I want you to go back and solve exercise 3, exercise 4 of the Redox chapter. After this, in-text exercise 3 and in-text exercise 4. Okay. After that, we will only need one more session to finish off the iodometric part. Okay. That's very specific part of Redox where we will use Redox to understand titration, where we'll use the concept of Redox to understand the quantity of certain substance which was used in the reaction or which was unused in certain reaction. So the redox application reactions are very amazing. They are I would call it very intricate. Let me just give an example of what I'm trying to say. um, you remember, you would have studied this, the photographic plates. They used to have like photochemical reaction takes place on the photographic plate. Now that photochemical reaction is basically decomposition of silver bromide. Have you heard this? Have you heard this have you studied this in your class 10th or before or somewhere? That silver bromide was used in the photographic plates. Nowadays we have digital camera. Everything happens on on our system itself. But initially we used to have silver bromide. It was briefly mentioned. Okay, in your books. Okay, no worries. I will tell you what exactly happens. So there's a photographic plate which is coated with multiple chemicals, but correct, Abhishek, you got it correct. I want everyone to try question number 13, 14 and get to the answer. Till then, I will just tell you this part. So the photographic plate, which has multiple layers of chemical on it, there's one very important chemical which is responsible for creating the image is silver bromide. Now, silver bromide, when exposed to sunlight or any kind of light, it decomposes into silver and bromine. So when your silver bromide decompose into silver and bromine, the part of the photographic plate on which the light was, just flashed for a very minute amount of time. That much exposed part underwent the reaction, which is basically decomposition of silver bromide into silver and bromine. Whereas that part of the photographic plate where no light fell or it was so less amount of time that light couldn't directly hit that specific part of the photographic plate. There no reaction will take place. So AgBr, silver bromide, remains as it is. Now what will happen when you take off this photographic plate? You won't let it expose to the to the light, and it goes into a washing. That's the word we used to use for developing a film, developing a photographic plate into an actually photograph. So in that washing process, whatever unreacted silver bromide was there, it is removed using a hypo solution which is called Na2S2O3 solution, or it is called developer solution. So developing solution would remove the unreacted silver bromide. Now once you have removed all the unreacted chemicals, okay, this image is actually imprinted on the gelatin of the photographic paper or photographic plate, and that is technically a negative because on the part, let's say I am wearing a white or a light colored t-shirt and a dark colored pant. So when my photo is taken, the light coming from my shirt, when it hits the same position or same area on the photographic plate, there a lot of reaction will happen. A lot of silver bromide will get decomposed to silver and bromine. So that part will look like a dark part, because on that part a lot of reaction has taken place. Whereas I am wearing a black pant, if my light coming from my pant hit on the same position on the photographic plate, obviously it's a black pant, so not so much light is coming from it, so there will be very less amount of reaction on that part. So that part of the image will look white, or it will look bright. So that's the reason why photographic film used to be called negative. So negative means it is showing opposite of what I am actually wearing, or of all the lights which are actually coming out of me. Now when you develop the negative, then what happens on the on the paper on which we are creating the image, the it's processed in such a way that the opposite colors are again recreated, and thereby we get that real photo. So in this whole process, I just told you about the chemical process of this whole steps, right? All the steps. But when we talk about quantifiable matter, right, then I will have to find out, okay, how much silver bromide is left on the plate, how much hypo solution will be required. Now can I use this hypo solution once again, or is it enough, or is it less, and how much silver bromide will get converted into silver? All these calculations are basically a very simple single question, which requires your understanding of redox, which requires your understanding of number of electrons getting exchanged while that redox is taking place, and your understanding of moles and molecular weight. Only then you can quantify this whole thing. So that's the reason why redox is technically an extended version of mole concept, or I would say it's technically a more deeper version of mole concept. Okay, but the point is it requires a little bit of your understanding of oxidation state. It requires a little bit understanding of the the ratio in which the compounds will react. It requires an understanding of the type of product that will be formed. So because of all these things, we studied the chapter redox after chemical bonding, because after chemical bonding now we know why any particular atom has a particular oxidation state, how it is dependent on the bonding and all that. Okay, now about the application of this chapter, you will get to see application in mole concept, in redox. In class 12th you will see application of redox in the chapter electrochemistry, and mostly in all the chapters of inorganic chemistry. So you will get to see application of redox everywhere. Okay, so in electrochemistry we will be using the quantifiable part of redox, whereas in the inorganic chemistry we will talk about the qualitative part of redox, like why a reaction is taking place, what exactly is happening. Whereas in electrochemistry we will just focus on how much of the reactant has to be taken so that we can create a certain cell with certain EMF value and all that stuff. Okay, coming back to your answer. So what I'm trying to say is redox has a very deep application in your chemistry. So 144144, that's the answer, huh? Amazing. So I just want
Sir,
you
could
to
you do this one?
this one. Sure.
Yes, sir.
So let us look at the question. Uh, in the reactant part, I can see the N2H4. It is hydrazine. Can you tell me the oxidation state of nitrogen in N2H4? Anyone?
-2.
Perfect.
-2.
-2. Amazing. Now nitrogen is going from -2 to 0, whereas iron in this case you can see is in +3 oxidation state on the left hand side, going to +2 oxidation state on the right hand side. Now when you are looking at this complex thing, it's definitely a complex molecule. That's why I just put it in a square bracket. We will get to study about these complex ions in the first chapter of class 12, the first chapter of inorganic chemistry of class 12, which is coordination compound. So in coordination compound or complex compound, we'll talk about these kind of compounds, how they are formed and their behavior. But as of now, all I need is the oxidation state. Now, how am I supposed to know the oxidation state? Well, I have to know that cyanide ion has to have -1 charge on it. So when I know that cyanide has -1 charge on it, that means 6 cyanide ions will have 6 minus charge on it. So 6 minus charge due to the cyanide ion and +3 of the iron. So the total charge on the ferricyanide, that's what it is called. So ferricyanide ion has total charge of 3 minus. Whereas on the right hand side, you can see there are again 6 cyanide ions. So that has not changed. But the iron which is along with them has changed from +3 to +2. That's why the outer charge, the total charge on the complex ion is 4 minus. Tell me, did you get this part? Did you understand this part? Perfect. Omkar, now your trouble is sorted. Iron's oxidation state in this compound. Awesome. Amazing. So now I think I have already broken down the whole thing for you. So iron getting reduced to from +3 to +2, nitrogen getting oxidized from -2 to 0. I think you can figure out the rest of the part. Is it okay? Or should I do it? Tell me. No one has said anything. You will try. Perfect. Amazing. That's encouraging. Amazing. So yeah, you guys try this, है ना? I think you should not get stuck anywhere. Cool. Let me now move on to the next part of this chapter. Okay, this is technically we are almost done with the major part of this chapter. Now we are going to do the same thing, apply the same concept. But tell me one thing: have you studied normality in mole concept chapter? When you were taught mole concept, did you study normality? Normality, yes or no?
Yes, sir.
Yes. How many of you remember normality? Raise your hand. Vaishnavi, Kriday, Vittal, Anirudh, Akash, Pranav, amazing. So I can see 16, 17 people have your hands raised. 20, amazing. So these many students remember normality, amazing. Okay, still I will just take you through that once. Okay. We studied molarity during mole concept because whenever we are carrying out a chemical reaction, the chemical reaction takes place in the form of a solution, in the form of a state where we have something mixed in a liquid, and those liquid solutions when mixed together will undergo a lot of chemical reactions. So for chemical reaction, we generally create solution. Now, solution can have different concentration. Like I used to say, like if I have a cup of tea, now some people might like cup of tea with 1 spoon of sugar, some might like cup of tea with 2 spoons of sugar. So what are we talking about? We are talking about people having cup of tea with different concentration of sugar. Now this concentration had to be converted into a usable unit, which is basically used on a day-to-day basis. So this concentration was then defined in the form of molarity, number of moles of any substance dissolved in 1 liter of solution. That is technically the concentration in terms of molarity. Now the problem was when you are solving questions using molarity. Now say I have HCl. 1 molar HCl is going to produce 1 mole of H plus ion when you put it in the solution form, or like it has 1 mole of H plus ion roaming around. Whereas 1 molar H2SO4 solution will have 2 moles of H plus ion roaming around the solution. Now the point is, I have to know how many H plus ion that particular molecule or compound is going to leave every time I create a solution out of it. If I have H3PO4, so 1 molar H3PO4 solution will have 3 moles of H plus ion. But think about it. If I have a very complex organic acid which has multiple H plus ion getting released from multiple position, do you think I can just sit down and just figure out all that by myself while I am working in an industry creating big molecules? I cannot. I don't have time for that. I don't have resource for that. And in most of the case, I won't have knowledge about the compound that I am dealing with. So to solve this problem, we came up with the concept of normality. लोगों ने बोला let it be, let molarity be. No one cares about the molarity. Let's suppose if I have an acid. Now that acid can have 1H plus ion, 2H plus ion, 3H plus ion or 10H plus ion. I don't know. Let me just introduce a term called N factor. Now what is N factor? N factor can be decided on the basis of multiple things. For acid base, it is simply the number of H plus ion. For redox reaction, it is the number of electrons exchanged. So the concept of N factor is simply to avoid getting into the qualitative part of a chemical, to avoid getting into, okay, is this molecule going to give off 3H plus ion, or is that molecule going to get reduced from +7 to +2? I don't know, right? So in such a situation, we needed we needed a direct understanding of the N factor, and that direct understanding of the N factor when included with molarity gives us normality. So I personally like this definition of normality, where normality is nothing but N factor into molarity. Now when you have N factor and molarity both multiplied and a unit is formed out of it, I will get normality. Now what is the beauty of normality? Well, if I have one normal solution of HCl, if I have one normal solution of H2SO4, or I have one normal solution of H3PO4, all the three will have same number of or I would say same moles of H plus ions released. So normality had to come up with a new word. Instead of calling it moles, they came up with a new word which is equivalent. So number of equivalents present in 1 liter of solution is called normality, right? Number of equivalents per liter of solution. So even its unit is equivalent per liter. Okay. So if you look at molarity, the term the unit for molarity is moles per liter. For normality, it will be equivalent per liter. Are you with me till this part? Are you all with me? Now, how do we get equivalents? Well, it's a very simple process. Like if we think about equivalents, equivalent is already a problem half solved. So let's say if I have one normal NaOH solution. Okay, now one normal NaOH solution, or say one normal CaOH twice solution, right? All of them will have how many OH ion? They will have one equivalent OH minus ion. That's it. One equivalent. Now I don't have to worry about it. I just have to, if I want to neutralize this solution, I will have to bring one normal HCl, one normal H2SO4, okay, in such a way that they will also have one equivalent of H plus ion. So equivalent is basically a way of introducing N factor with the moles. So if I just look at this formula, normality is molarity into N factor. Can I say equivalence is equal to moles into N factor? Think of it. When you were not told about the concept of normality, every time you made a reaction between H2SO4 and NaOH, Okay, now both of them were 0.1 molar solution and 100 ml. So first you found out moles of H2SO4, then you found out moles of NaOH, right? And once you had moles of H2SO4 and moles of NaOH, then you would say, oh, for every H2SO4 molecule, you will require 2 moles of NaOH. Why? Because H2SO4 has 2 H plus ion, NaOH has only 1 OH minus ion. But when it comes to molarity, you have to do all this stuff. So when we are doing, let's say we had a 0.1 molar solution, 100 ml solution. In this case, 0.1 molar, 100 ml solution, right? So, sorry, let's say volume of this is not given. Okay, and you are supposed to find out volume of the H2SO4 required. So 0.1 molar, 100 ml, zero point 0.1 molar, x ml. So when you went with the, basic formula of M1V1 is equal to M2V2, right? How did we introduce this formula? M1 into V1, molarity into volume was technically number of moles, right? Similarly, molarity into volume for NaOH will also give you number of moles. But the problem is I have to introduce the N factor as well in this case, because H2SO4 one molecule will produce 2H plus ion. Now to keep that into consideration, I will have to multiply M2V2 with 2 so that my molarity will give me the answer how much volume of H2SO4 is required. But people solved all this stuff. People said, "Arey yaar, screw this. क्यों इतना सब करना है? Let's keep everything simple." So when you have things in terms of normality, you don't have to worry about number of H plus ion. You don't have to worry about number of OH minus ion. You don't even have to worry about the number of electrons being exchanged. In case of normality, you will simply get N1V1 equal to N2V2, because what are we equating now? We are equating equivalence. The name itself suggests that equivalence of first solution, equivalence of second solution, you just make it equal, your problem is solved. Are you with me till this part? I suppose you all know this part, but still I just wanted to reiterate it in my own way. Now, N factor is dependent on the number of H plus or OH minus in acid or base. Okay. So if you have H2SO4, N factor will be 2. If you have H3PO4, N factor will be 3. If you have AlOH thrice, N factor will be 3. So this is first thing. Second is, it is dependent on number of electrons exchanged. Now this is very important for us from the perspective of redox reaction, because the N factor, if you are given everything in molarity, you should be able to convert it using N factor into normality. Okay, so if we just talk about N factor, then N factor for, let's say, I will give you a very simple reaction. MnO4 minus. We did this oxidation reaction using KMnO4, where MnO4 minus got converted into Mn plus 2. Now this is generally what happens in an acidic medium. In acidic medium, Mn will jump from plus 7 oxidation state to plus 2 oxidation state and will technically absorb 5 electron. So can I say N factor for MnO4 for this reaction will be 5, because what is N factor? Number of electrons exchange. Are you all with me till this part? Yes or no? Is it clear?
Yes, sir.
Amazing, amazing, amazing. So say I have a compound H2C2O4, and you know after oxidation it is going to convert into CO2. I want to know N factor for H2C2O4. Can you tell me the N factor for H2C2O4?
1 second.
Beautiful. Pranav, Praveen Kumar. Amazing. Abhishek, Pranav,
So
Omkar,
there is
also.
no positive or negative thing, right, in any factor.
नहीं, N factor में there is no positive or negative thing. N factor is just basically a normalizing factor. So, you don't have to worry about the number of change and all that. Now, I know that MnO4 is going from MnO4 plus 7 to plus 2. Imagine some complex organic compound getting oxidized or reduced. Now, you cannot just keep on sitting and writing down, Acha, this carbon went from plus 3 to plus 2, but that carbon went from plus 3 to plus 4. How many carbons are going from this to that? That will be done for you. So what you will get? You will get simply the N factor for this compound when undergoing oxidation reaction is 6, 8, 9, whatever. It can be a number. It's just a number or it's simply a multiplier. Okay. Amazing. Guys, all of you I think have got the answer correctly. You can all see, right? In this case, carbon is going from plus 3 oxidation state to plus 4 oxidation state. Now, every H2C2O4 molecule has 2 carbon atoms going from plus 3 to plus 4. So, I will say every H2C2O4 molecule is going to release 2 electrons. And if it is going to release 2 electrons, obviously someone will get those 2 electrons. But what I care about is it's the N factor for this reaction, and that is simply 2. All of you got this? Yeah? Now let me tell you something very interesting. Permanganate is a very weird one. Okay, we'll talk about that later. Let me know the N factor for K2Cr2O7. Now you will be like, अरे sir reaction तो बताओ. नहीं बताएगा. I want you to remember, try to recall potassium dichromate. We have done a question on this. Yes, potassium dichromate. After reaction, I will just give you a very simple hint. It goes into plus 3 oxidation state. Chromium goes into plus 3 oxidation state after the reaction. You just have to tell me the N factor for potassium dichromate. Abhishek, Pranav, Shivardhan. Hey, Shivardhan, C is here. Good. And did you
Yes,
join?
sir. Yes, sir.
Where
My
were you?
bad. I didn't realize.
ठीक है, no worries. So I think all of you got the correct answer. Look, Shivardhan, D, Akash, Pranav, Vittal, Anirudh. Amazing guys. Amazing. Girls, where are girls? Come on, I need answers from girls as well. Are you busy with something? Yes, amazing. Niyantri, Meera. Superb. The oxidation state of chromium in K2Cr2O7 is plus 6. And from plus 6, it will go into plus 3 oxidation state. So there will be a change of 3 electron for every chromium atom. Now, how many chromium atom we have in this case? We have 2 chromium in 1 dichromate ion. So 2 chromium atoms going from plus 6 to plus 3. So total number of electrons that will get exchanged will be 6 electrons. So the N factor for this one will be 6. Amazing. Anyone any doubt with this? If you have any doubt regarding this, please let me know, guys. Please let me know. This is like one of the most basic concept that we have to understand. Now I am going to give you a very interesting thing. Okay? Potassium permanganate behaves in a very weird manner in presence of acid, in presence of base, and in presence of a very strong base. Okay. Now I will just tell you the end product for each of these cases. What you are going to do, you will tell me the N factor for each of these cases. So when you have strong you have acidic medium in general. If you have an acidic medium, the MnO4 minus will go into Mn plus 2. MnO4 minus will go into MnO2 when the solution is neutral or mild basic. whereas MnO4 minus will go into MnO4 2 minus when the solution is strongly basic. What you are supposed to do, you are supposed to tell me n factor for each of these cases. Come on. And by the way, guys, everyone, right now you are all here. All of you, please open the YouTube and just give me a like. At least give a like on the video which is going on live. For that is very important, you know, right? Because we are going to create a lot of things on YouTube. So a lot of things are coming from, especially your batch. You know, you are my YouTube batch. You are my first, you know, YouTube plus live combo, like deadly combo batch. So I want all of you to please increase the likes on all the YouTube videos which I'm creating for you. Okay, that's the least I can expect from you, right? Cool. Answers amazing. Akash, Kaustubh, Anirudh, Pranav, Vittal, Srivardhan, Aditi, amazing. So in first case, the number of electrons getting exchanged are 5 electrons. In second case, the number of electrons, you can see it is going into plus 4 oxidation state. The number of electrons getting exchanged are 3 electrons. In the third case, it is going into plus 6 oxidation state. So the number of electrons exchanged is 1 electron. So n factor for first case is 5, second case is 3, and the third case is 1. Amazing. Superb. I still have not got everyone's like on the video. Come on, please do this fast. Thank you so much. I can do this, right? I can just make the, if you have liked the video, then your attendance is done. Something like this. Yeah, but let's not do that right now. Okay, okay, we have 31 students today. Okay, I think everyone who was present yesterday is present today as well. Because when I took the attendance initially, this is the full attendance. Amazing. Chalo, ठीक है. So I will just show you something. Yeah. So guys, I suppose you are all able to see the exercise over here. Exercise 2. You were supposed to do it today, but if you have not, then please try to do it before the next session. Okay, just take out some time. Then you can now start doing the exercise 3 as well. Okay, before you start with exercise 3, you can see in our modules we have the equivalent weight or the n factor. Now just to introduce you to the equivalent weight part, you can see that equivalence is equal to moles into n factor. Similarly, if you want to just find out equivalent weight with respect to molecular weight, then equivalent weight is molecular weight divided by n factor. So you can remember just either of it. I personally like to remember the normality one. Normality is equal to molarity multiplied by n factor, and that way equivalent is equal to moles multiplied by n factor. That is the one I try to remember most of the time. So to avoid getting confused, now I can derive from that part what is equivalent weight. The equivalent weight is basically going to be there in the denominator part, because for finding out moles we say mass upon molar mass. So in case you have to find out the equivalence, you have to get it as mass upon equivalent weight. So that's how you can just derive that the n factor when you are considering from the perspective of molecular weight or molar mass. It is molecular weight divided by n factor giving you the equivalent weight, and that is what is mentioned in this table, as you can see. So for different compounds, you can find out the equivalent weight by yourself. It is simply the change in oxidation state number of electron exchange, you got the n factor, and then you got the rest of the thing. So I am very sure you can now solve exercise 3, and I want you to continue to this part as well. Okay, like we can use the law of chemical equivalence, just like we use molarity. Now we can use normality, and I want you to just see if you can try solving questions from exercise 4 as well. 4 is not technically homework, but I think you are capable of solving exercise 4. Okay, so next time when I meet, I will definitely discuss exercise 3 and exercise 4. And after that, we are just left with one more exercise. In that part, we will discuss about the. Okay. Why did this happen to me? Yeah, don't worry. I think there is only 4 exercise. There's no 5th exercise. After this, you will be like exercise will be starting exercise 1, 2, 3. So yeah, we'll be done with this in the next class. That's all for today. Thank you so much for being here. I suppose all of you have liked the YouTube video. If you have not, please do not forget to like it and also subscribe the YouTube channel. And if you have any other doubts, anything that I have maybe not covered or not answered, you can message it to me. Okay. Thank you so much.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you, sir. Thank you, sir.
All the best for your paper.